Welcome to the Explainer. Today, we're going to decode vector algebra. It's kind of the secret language that powers everything from the physics in your favorite video games all the way to navigating spacecraft. So let's just dive right in. So let's start with a question. What's the real difference between a football pass and, say, your height? I mean, one is just a measurement, right? But the other one, it has direction, it has a purpose, a target. And that single difference, right there, that's the core idea behind every single vector. To really get a handle on this, we need to meet two key players in the world of physics and math. On one side, we've got scalars, and on the other, the star of our show today, vectors. Look at it this way. Your height is a scalar. It's just a number, a magnitude, let's say 1.6 meters. That's it. Simple. But that football pass? That's a different story. It's not just about the power of the kick. That's its magnitude. It's also about the direction. And that combo, magnitude plus direction, is what makes it a vector. Honestly, the absolute easiest way to picture a vector is just as an arrow. The length of that arrow, that's the magnitude, the how much, like the force of that kick. And the arrowhead itself shows the direction, the which way, aiming right for your teammate. Okay, so we've got these arrows kind of floating around in space, but how do we actually describe them with numbers? How do we give them a precise mathematical identity? Well, the secret is to break them down into their components. In our 3D world, a vector's unique identity, its DNA, if you will, is totally determined by how far it reaches along the x, y, and z axes. These values are its essential building blocks, its components. And here on this slide is the recipe. This component form is just a simple set of instructions. It's telling us, hey, move x units along the I direction, y units along the j direction, and z units along the k direction. Now these letters I, j, and k, they're just our standard road signs. They're special little vectors called unit vectors that perfectly point the way down the x, y, and z roads. It's simple, it's elegant, and it's incredibly powerful. All right, so now that we can describe these things, let's actually have some fun with them. It's time to see what happens when we start combining them. This is where the magic really starts to happen. I want you to imagine you're walking down the street. You go 3 blocks east, then you turn and walk 4 blocks north. Each part of that journey is a vector. Vector addition is what finds you the shortcut, that single, direct path from where you started straight to where you ended up. Now, what's really cool about this slide is that it shows 2 different visual tricks for finding that shortcut. Over on the left, with the triangle law, we place the vectors head to tail, like you're continuing a journey. On the right, with the parallelogram law, they both start from the same point. But check it out. They both give us the exact same result. It's 2 different ways of looking at the same problem, leading to the same truth. Next up is scalar multiplication. It sounds kind of complicated, but it's actually dead simple. All we're doing is stretching or shrinking a vector. You multiply it by 2, and just like you see here, it just doubles in length. Multiply it by -1, it keeps its length but does a complete 180 and flips its direction. That's it. Okay, this brings us to the big one, the most powerful and, let's be honest, the most surprising part of vector algebra, multiplication. See, with regular numbers, multiplication is pretty straightforward. 3 times 4 is always 12. End of story. But with vectors, it's a completely different ballgame. There isn't just one way to multiply them. There are 2, and each one answers a totally different kind of question. So first up, we've got the dot product. This thing takes 2 vectors and gives you back just a single number, a scalar. Then we have the cross product, which takes 2 vectors and, get this, it gives you a brand new vector. The whole point of the dot product is that it measures alignment. Imagine you're shining a spotlight along one vector. The dot product tells you how much of a shadow the other vector casts in that direction. And here's the really cool part. If the dot product is 0, it means they're at a perfect 90-degree angle to each other. They cast no shadow at all. The cross product is a whole other beast. You should think of it like a vector factory. You feed in 2 vectors that are just sitting there on a flat plane, and it spits out a completely new vector that points straight out of that plane, perfectly perpendicular to both of the ones you started with. So how in the world do we know which way this new vector points? Up or down? Well, that's where this brilliant little trick comes in, the right-hand rule. Just point your fingers in the direction of the first vector, curl them toward the second one, and wherever your thumb is pointing, that's the way. It's like a built-in biological calculator that you always have with you. So why does any of this matter? Because vectors aren't just some abstract math concept. They are literally the language our world is written in. The forces holding a bridge together? That's vector addition. The lighting and shadows in your favorite video game? That's the dot product at work. The torque on a spinning engine? That's the cross product. From engineering to plotting a course to Mars, vectors describe how everything moves and interacts. So, from a simple football pass to the complex systems that shape our reality, you now have the tools to see the world in terms of both magnitude and direction. You've basically been handed a new lens to look through. So the question is, where will you spot a vector hiding in plain sight?